Okay, so VCAA has published the NHT math paper, including method, special, and general. I'm going to give a crack at this math method exam 1. So let's have a look. Question 1, 4 marks. First one is a quotient rule. So make u equals to log ex, and u dash is 1 over x. V equals to x to the power 3. So v dash is 3x squared. And my dy dx is going to be u dash v minus v dash u over v squared. So I'm going to get 1 over x times x to the power 3. Take away 3x squared times log e of x. And I write the long vinculum, x to the power 3 squared, that is x to the power 6. So you can actually get, let's say on the top, x squared. Cancel that, you get x to the power 2 minus 3x squared log ex divided by x to the power 6. Just notice there is a phrase called simplify. So I take out a common factor, x squared minus 1 minus 3 log e of x divided by x to the power 6. So you get a 1 minus 3 log e of x divided by x to the power 4. So that is a simplified answer. Or you could use product rule or use a different color. Say your dy dx is the derivative of the first, that is minus 3x to the power minus 4 times log e of x plus x to the power minus 3 times the derivative of log ex. That is 1 over x. So eventually you get a minus 3 log e of x divided by x to the power 4. And this would be plus 1 over x to the power 4. Because 1 over x to the power 3 times 1 over x is just a 1 over x to the power 4. Eventually it's the same thing. The question says simplify, so try to keep your term one single term or two terms, the simplest, but the question didn't say one single term. I don't know. Anyway, next one. F of x is sine pi e to the power 3x. Evaluate f dash 0. Chain rule. You might want to say, okay, derivative of sine g of x, if gx is differentiable, is equal to the derivative of the inside times the derivative of the outside. So derivative of sine is cosine, and the inner function is still g of x, okay? That means the g of x is this pi e to the power 3x. So my f dash of x is going to be pi times 3e to the power 3x. You need to find the derivative of the inside times cosine of, actually I don't have 3 here, just pi e to the power 3x. So don't write an extra 3 inside. And then you get f dash of 0, that is pi times 3 times e to the power 0 times cosine pi e to the power 0. And you may get 3 pi, this is a 1, and cosine pi, if you draw a unit circle, it's up to here, okay? So it's negative 1. Therefore, it's negative 3 pi. So that's the final answer. Okay, yep, this is question 1. Okay, function g of x is a cubic function, ax cubed plus bx squared plus c. A, b, c are real numbers. H is x squared divided by 4. Graph of g, it passes through the point 0, 9. graphs of G and H pass through the point 69 and have the same gradient at this point. These two graphs shown below, find the values of ABC. So one thing is, if you use this condition, we say G naught equals to 0 plus 0 plus C equals to 9. Therefore, C equals to 9 and G of x equals to ax to the power 3 plus bx squared plus 9. And the next thing is you need to use, let's say, 6, 9, because that point lies on this cubic. So you say G of 6 equals to a times 6 to the power 3 plus b times 6 to the power 2. I'll put bracket around them, plus 9. And it equals to 9. So actually you will get 6 squared times 6 times a plus 6 squared times b equals to 0. So you could say, all right, divide everything by 6 to the power 2, you get a 6a plus b equals to 0. So b equals to minus 6a. But you still need another equation to find a and b values. Therefore, you probably need the same gradient to find, let's say, the other equation. So I'll take g dash of x equals to 3ax squared plus 2bx, and h dash of x equals to 2x divided by 4. That is x over 2. So g dash 6 equals to h dash 6, equal gradients. And into that, I have 3a times 6 squared plus 2b times 6 equals to 6 over 2. That's a 3. So eventually you can cancel a 3 both sides. For example, you say 36a plus, let's say if I divide everything by 3, that's 2 times 2 is 4. 4b equals to 1. And just notice you have another equation here. I'll call this equation 1. This is equation 2. So if you substitute 1 into 2, say 36a minus 24a equals to 1. So 12a equals to 1, and a equals to 1 out of 12. Therefore, your b equals to minus 6 out of 12, which is minus half. Eventually, you want to write the answers carefully. So you say, therefore, a equals to 1 out of 12, b equals to minus half, and c equals to 9, etc. Okay, the question didn't ask for the rule, so we can just write down the a, b, c values, etc. Okay. F of x is half tangent x plus half d is the maximal domain. So the maximal domain, I suppose, is like this. Well, let's write it like d belongs to r backslash half pi plus k pi, and the k belongs to any integers, something like that. So these expressions represent the vertical asymptotes. Find a general solution for fx equals to 0. So you have half tangent x plus half equals to 0, and the tangent x equals to minus 1, okay? So x can have minus pi over 4, but if you think about a quadrant, minus pi over 4 is here. This is quadrant 4. This is quadrant 2, negative value. So each half term, the tangent value repeats its value. So you add a k pi, where k belongs to integers. Or if you chose, let's say, to start with a 3 pi over 4, that's fine. I'll put an alternative answer here. Okay. Usually amongst my students, it's not uncommon for them to write things like x equals to minus pi on 4 plus 2k pi. But the problem with this expression is you only get let's say each full term. So you will go past this solution here. Okay, you bypass the solution in the middle. You can't just add a 2k pi because the period of tangent is pi. Okay, so if you really want to include, let's say 2k pi, you really have to include another solution. And these two expressions together can be combined into either this one or this one, okay? So for tangent general solution, we add k pi rather than 2k pi because the value repeats each half term. I don't want this to confuse you. So let's move on. G is sine x plus half. Find all values of x such that fx equals to gx for x between minus pi to pi. Okay. First of all, I equate these two equations. Half tangent x plus half equals to sine x plus half. Just cancel them out. Half sine of x divided by cosine of x equals to sine x. It is so tempting to divide everything by sine x, but don't do that because what if you divide everything by 0? That's meaningless. And in fact, this sine x term may well be 0. So what I will do is I'll multiply both sides by 2 first. And then I will rearrange everything like sine x divided by cosine x minus 2 sine x equals to 0. And I'll bring out sine x as a common factor, multiply by 1 over cosine x minus 2 equals to 0. So sine x equals to 0, and cosine x equals to half, okay? And between, actually, minus pi, between minus pi and pi, you can't really take minus pi or pi, but you can take 0. So your sine value is 0, or cosine value pi on 3, that is 1/2. And in the fourth quadrant, cosine is also positive. So you get x equals to plus or minus pi on 3. In this case, we have a restricted domain, so we don't need general solution. We need the particular solutions, okay? The graph of y equals to gx is shown below. On the set of axes below, sketch the graph of y equals to f of x over this interval. You can see these two values, plus or minus half pi, they are round brackets. That also implied the vertical asymptotes. So the very first thing, I'll label the asymptotes with their equations and draw them. Make sure you use dashed lines and a ruler. For example, like that. Like that. Then I guess the reason why they provided y equals to f of x here is previously you worked out, let's say f of x equals to g of x, and it provides you x equals to 0. So they intersect at x equals to 0. This is definitely 0/2. Okay. And also you have plus or minus pi on 3. So look at the number of grids here. You divide half pi into 3 pieces. So this is a pi on 6. This is a pi on 3. This is a minus pi on 6. This is a minus pi on 3. So basically, if you look at the pi on 3 mark, you definitely have the second graph cutting through this point and also this point. So this is very important, and you probably need to be very accurate on this aspect. And I know this is going to be minus pi on 3 something. And I know this is going to be, let's say, pi on 3 something. I can do a substitution later. Then I say this is x equals to half pi, and this is x equals to minus half pi, okay? Just be aware. your g of x equals to sine x plus half, if I'm not mistaken. So g of pi on 3 is sine pi on 3 is root 3 on 2 plus half. And the g of minus pi on 3 is going to be minus root 3 on 2 plus half. So actually, for this value here, I can write 1 take away root 3 divided by 2, exact values only. And this is 1 plus root 3 on 2. And also, you notice there is a general solution like tangent x equals to minus 1 coming from f of x equal to 0. So one particular solution within this domain will be minus pi on 4, which is in the midway here, okay? I will label this anyway. And notice the symmetry, ladies and gentlemen. Like, this is a point of inflection. You get a tangent graph, something like that. But what I'm going to do is I'll also recognize, let's say, a symmetrical point from here to here, from here to here, okay? This is called the rotational symmetry. All right, I've got all of this. Got all of this. So I'm going to just make it clear to you. So these will be the key things I mark on my set of graphs, okay? And then I'll just get a nice graph. Okay, something like that. So this blue graph is my y equals to f of x. Finally, let's do a check. Labeling all points where f of x equals to gx with their coordinates, all asymptotes with the equations, the shape, yep, pretty much everything you could ever ask for. Okay, contains a large number of apples. 1/3 of the apples are bruised, okay? In the random sample of 4 apples, so n equals to 4, and our probability of a bruised apple is 1/3. So let's call x a binomial distribution, n equals to 4, p equals to 1/3. We like exactly 3 bruised. So we have probability of x equals to 3, 4 choose 3, 1/3 power 3, and 2/3 power 1. Make sure you realize the index, the two indices will add up to 4. And then you have 4 choose 3 is just 4. Remember, n choose 1 equals to n choose n minus 1. That's n, okay? Times 1 out of 3 to the power 3 times 2 divided by 3. So you actually get 8 divided by 4, 3 to the power 4. That is 8 divided by 81. Let p hat be the random variable representing the proportion of bruised apples in the random samples of 10 apples. Okay, p hat. P hat is less than or equal to 1/10. So this time we have n equals to 10, but p is still 1/3. Let's call y is another binomial random variable, n equals to 10, p equals to 1/3. Okay, so I would like to get, by the way, p hat equals to y divided by 10. Therefore, if I multiply everything by 10, you will get y less than or equal to 1. Okay, y is less than or equal to 1. So that is actually y equals to 0 plus probability y equals to 1. For 0, a bruised apple, that is 10 choose 0, 1/3 to the power 0, and 2/3 to the power 10, plus 10 choose 1 times 1/3 times 2/3 to the power 9. Eventually, you get 2 to the power 10 because this is a 1, this is a 1, divided by 3 to the power 10 plus 10 times 1/3 times 2 to the power 9 divided by 3 to the power 9. And this is 2 to the power 10 divided by 3 to the power 10 plus 10 times 2 to the power 9 divided by 3 to the power 10. So eventually we can just, let's say, combine 2 parts into 1. The question wants you to give the answer in this form, so it's definitely possible to simplify the two terms. So I'll write 2 to the power 10 like 2 times 2 to the power of 9 plus 10 times 2 to the power of 9. And we can get a common factor divided by 3 to the power 10. And you take out 2 to the power 9. 2 plus 10, that's 12, divided by 3 to the power 10. And you get 2 to the power 9 times 12, divided by 3 to the power 10. And just a few more steps. You can only retain a base 2 and a base 3. So I'm going to do 2 to the power 9 times 2 to the power 2 times 3. This is the prime factor expansion of 12 divided by 3 to the power 10. So you can actually see you cancel out the 3. This is 3 to the power 9 now. And the top number is 2 to the power 11. For example, your n value is 11, n value is 9. Okay, so that's pretty much option part B. Question 5. Okay, point of intersection between f and g. X value only. You don't have to find the y value, I suppose. So we say f of x equals to e to the power x. We don't need that actually. I just equate them directly. E to the power x equals to e to the power x plus 2. And this is definitely a hidden quadratic. So we write e to the power 2x as ex squared minus ex minus 2 equal to 0. E to the power x, e to the power x minus 2 plus 1. So you have e to the power x take 2 and e to the power x plus 1 equals to 0. And you get e to the power x equals to 2 or e to the power x equals to minus 1. Definitely impossible. Because if you look at the shape of e to the power x, it's larger than 0. So knock that out. Therefore, your x is log e of 2 only. If you write ln of 2, that is fine because ln is a conventional notation for log base e. But if you write log 2 without base e, I don't think it's quite right. It's not like chemistry. In chemistry, they do have their convention. Like in chemistry, everyone knows pH is minus log H23 plus H3O plus. The negative logarithm of the concentration of hydronium ion. But in this particular case, it's a conventional thing, log base 10. If you don't write any base, that defaults to log base 10, okay? So you have to, in my opinion, in math method and specialist math, you need to write the base number. Okay, find the x value where the graph of y equals to f of x and y equals to g x minus y have equal gradients. Equal gradients, so derivative of f is 2e 2x, and the g dash of x is going to be e to the power x. So g dash x minus 1 is simply ex minus 1. So I'm going to equate them and find the x value. 2e 2x equals to ex minus 1. And then what I'm going to do is I'll write 2 times e to the power 2x equals to e to the power x divided by e. Then I'll combine the ex and e2x terms, like e to the power 2x divided by ex equals to 1 over 2e. The reason why this time I can divide it by ex compared to the previous example, the previous question, I couldn't divide everything by sine, is because ex is larger than 0. Yes, you can divide it through, okay? And then I can simplify everything to ex equals to 1 over 2e. So take the natural log. X equals to log e 1 over 2e. Of course, you might, let's say, see other variations. Probably can show you another possibility, like some creative approaches could be e to the power log e of 2 times e to the power 2x equals to ex minus 1. Just write the 2 as e to the power log e2. Then you get e to the power 2x plus log e2 equals to e to the power x minus 1. Both sides have the same structure. Both coefficients are 1. And you can just equate the indices. Say 2x equals 2x plus log e2 equals to x minus 1. So subtracting x both sides. And you get, let's say, x equals to minus 1 minus log e2, which is equivalent, I would say, because you can combine these two terms into that. So they are equivalent. Okay. Oh, I'm not going to go through method 3. Otherwise, I'll be running out of time. So I just move on. But there are other possibilities, okay? Okay, question 6. A high jumper has up to 3 attempts to jump over a bar at a specific height. Once one attempt is successful, the high jumper does not make another attempt at this height. So at this height, let A be the event that the high jumper's first attempt is successful. Let's make a start. Success. So this is actually my first event. Probability A is 0.6. If I failed, I can make another attempt. And up to here, I don't have to make any other attempt, okay? This is also fail. And we might also get, let's say, success or fail. So B is the event that the high jumper's second attempt is successful. Okay, so if I say B given A is 0.5, let's look at the first branch. This is 0.4, the other case. And given that A dash fail is, this first fail is A dash, and then B given A dash, this is 0.5, then you also get a 0.5 here. All right, let n be a discrete random variable representing the number of attempts the high jumper makes at this height. So you could say this bit is A, and this branch and this branch altogether, it's B, okay? Success or failure. Actually, sorry. B should just be, this case, because if you fail the second time, you can still go for, let's say, another attempt, okay? Anyway, yeah, if you only make 2 attempts, that means your second must be successful. That makes sense. So 2 successful, that the second time successful is 0.4 times 0.5, which is 0.2. And the last one, because this is a probability distribution, you have to add up to 1, all the probabilities. So this is 0.2. And then you find the mean number of attempts the high jumper makes at this height. Okay, so E of n is 1 times 0.6 plus 2 times 0.2 plus 3 times 0.2. So you get a 0.6 plus 0.4 plus 0.6. Therefore, you get a 1.6. Or if you worked with fractions, 1.6 is equivalent to 8 over 5. Okay. The high jumper was not successful on the first attempt at this height. Find probability C given B dash, given that the high jumper has a 0.7 probability of making a successful jump on either their second or third attempt. So this is, in my opinion, a hidden conditional probability. This is my condition. The key idea is reduce your sample space. So if you reduce your sample space, let's have a look at this diagram. Let me just knock out this thing here. Well, the branch I circled in blue is event A. Then everything else will be A dash, okay? This includes 0.4 times 0.5, 0.4 times 0.5 times this one. Actually, this is probability C given B. We call it X here. Then this must be 1 minus X, okay? And if that sentence was stipulated, then I only look at my new sample space. So I don't have to use the conditional probability statement like probability of A given B is like probability of A intersecting B divided by probability of B. I'm not going to look at that. I'm just looking at the reduced sample space. Then within this reduced sample space, the high jumper has a 0.7 probability of making a successful jump on either second or third. So you could get, let's say, that 0.4 times 0.5. Or let's say 0.4 times 0.5, 0.4 times 0.5. Times X plus, do I need to add? No, just a second or third success over, let's say, 0.4, okay? And then it is equated to, let's say, 0.7 divided by, actually, this 0.7, yeah, this is 0.7, yeah. Because you can just knock out the 0.4, isn't it? So eventually, you get a 0.4, 0.5 plus 0.5 times X divided by 0.4 equals to 0.7. Okay, this is your final probability. Cancel them out, you get a 0.5 plus 0.5x equals to 0.7. And 0.5x equals to 0.2. So x equals to 0.4. Okay. Therefore, your probability of C given B dash equals to 0.4. Problem solved. And the reason why I was a bit hesitated to divide 0.7 by 0.4 is because this is already a conditional probability. And think about 0.7 over 0.4, that is a number larger than 1. It's, it's crazy. It's just nonsense, okay? Alternatively, you can just ignore the 0.4 and say, okay, 0.5 plus 0.5 times x equals to 0.7. the problem can be also solved easily. All right. Question 7. This is a function. Find the values of b for which the two solutions of that have a difference of 5. So the two solutions, we could say x equals to minus b plus or minus square root b squared minus 4 times 1 times minus 6, so plus 24 divided by 2. Difference is equal to, let's take the larger one, subtracting the smaller one. Be aware of the plus or minuses, okay? And you can see that minus b plus b cancelled, and a minus sign is plus sign. So eventually it's b squared plus 24 over 2 plus square root of b squared plus 24 divided by 2 equals to b squared plus 24 under the square root. It's equal to 5. Well, technically speaking, you could also use the negative one to take away the positive square root expression, but you're gonna square both sides anyway. So you could say square both sides, b squared plus 24 equals to 25. So b squared equals to 1. B is plus or minus 1. Some would use, let's say, a thing called the Vieta's theorem. Like x equals to alpha beta 2 ax squared plus bx plus c equals to 0. Then you would get, let's say, alpha plus beta equals to minus b over a, and alpha times beta equals to c over a, something along this line, okay? This is also a possible method. So let x equals to alpha beta be the solutions to, let's say, x squared plus bx minus 6 equal to 0. So you could say minus alpha plus beta equals to boy. And alpha times beta equals to negative 6. For example, if you square the first one, it gives you alpha plus beta squared equals to b squared. And note that alpha plus beta squared minus 4 alpha beta equals to alpha minus beta squared. So this is like an identity. And then you say, okay, this bit is b squared, and minus 4 times alpha beta, that's minus 6, equals to alpha minus beta, that is a difference of 5. So you can say 5 squared. Therefore, b squared plus 24 equals to 25, and b squared equals to 1. So b equals to plus minus 1. Something along these lines. Yep, it's also a possible method, but less common to most of the VCE students. Okay, let b less than 0. Explain why an inverse function does not exist when f is restricted to the domain 0 to infinity. In fact, if you complete the square, f of x is x squared plus bx. I can add a b squared divided by 4 minus 6 minus b squared divided by 4. B squared divided by 4 comes from b over 2 whole thing squared. So you have x plus half b squared minus, let's say, 6 plus b squared over 4. Of course, I'm going to put a bracket here. Therefore, the stationary point is minus b on 2. and the minus 6 plus b squared over 4. Okay, so if b is less than 0, then x stationary point equals to minus b on 2 must be larger than 0. But this is definitely less than 0. So y stationary point is minus something. So it's just a negative value. We know the graph is going to cut through, let's say, minus 6 somewhere. It's a parabola, isn't it? So if the domain is 0 to infinity, this is my minus b on 2 if b is less than 0. This is the stationary point. It's a many to 1 function over 0 to infinity x value. That's why the inverse function does not exist. But if you look at the next part, find the rule for the inverse function of f when f is restricted to the domain minus infinity to 0. This part, it is indeed invertible because it's a one-to-one function. So I'm going to use the complete square form to make our life easier. Let x equals to y plus half b squared, take away 6 plus b squared over 4, or inverse. So we say x plus 6 plus b squared over 4 equals to y plus b on 2 whole thing squared. We can take plus or minus x plus 6 plus b squared over 4 equal to y plus half b. Then we take a look at the choice. Do I take the positive or negative square root? As domain of f equals to the range of f inverse equals to minus infinity to 0. This y equals to f inverse of x must be less than 0, okay? So we say y equals to f inverse of x equals to the negative square root x plus 6 plus b squared over 4. Take away half b, okay? And the domain restriction should be, let's say, x belongs to minus 6 to infinity, okay? Because if you look at the diagram we just drew above, it's starting from here to here, okay? Yep. Okay, let G be a function with maximal domain and the rule Gx equals to log e minus x minus 2. Find the value of b for which the maximum domain of the composite function g of f is minus 2 to 2. Okay, so it's this guy here. G of f of x equals to log e of minus f of x minus 2. So it's log e minus x squared plus bx, take 6, take 2. So you will get a log e of plus 6 minus 2, that's a 4. Take away bx, take away x squared. Okay, so if this is defined, we need 4 minus bx minus x squared greater than 0, something like that. Now, on the other hand, the maximal domain is minus 2 less than x less than 2. So you might say, okay, if you square everything, that will give you x squared is less than 4. And you could say 0 is less than 4 minus x squared. So you would get 4 minus x squared is greater than 0. Aha. So when you compare them, you could say, all right, this one doesn't have x term. Therefore, b equals to 0. Something along this line. Alternatively, yeah, we used some kind of, difference between the two solutions equals to something. We say alternatively, once you get, let's say, the log E4 minus Vx minus 4, x squared, consider 4 minus bx minus x squared equals to 0. So you get x squared plus bx minus 4 equal to 0. And then x equals to minus b plus or minus square root b squared plus 16 divided by 2. So the difference equals to, just cancel out a minus half b, you get a square root b squared plus 16. And it should be, let's say, yeah, 2 minus minus 2 equals to 4. So b squared plus 16 equals to 4 squared equals to 16. Therefore, b squared equals to 0, okay? And the b equals to 0. So that is another method. If you make a link back to the previous part. Alternatively, you could also argue that you can complete a square as x is between minus 2 to 2. The turning point of 4 minus bx minus x squared must be x equals to 0. This is just symmetry. Therefore, bx term equals to 0 and b equals to 0. Something along this line. As long as you explain yourself clearly with convincing correct mathematics. All right. Question 8. Okay, this is an interesting one. X divided by 2 root x plus k. K is a positive real number. K greater than 0. Consider the particular case where k is 6. Show that ddx x times root x plus 6. Okay, very simple. So if you just take the derivative of root thing, that is 1 over 2 square root x plus 6. Therefore, when you take the derivative of x times square root of x plus 6, this is just 1 times square root x plus 6 plus x times 1 over 2 square root of x plus 6 product rule. Then you get x plus 6 plus x divided by 2 square root x plus 6. This is a short question that provided you, let's say, 7 lines. Well, you might want to show this explicitly, but if you can just see this through, make sure you have a setting out of, let's say, product rule, I would say. That is a half times x plus 6 to the power minus half times 1. So it's 1 over 2 square root of x plus 6. Some are working like that, okay? For me, I just know it by heart. Hence or otherwise, evaluate the definite integral 0 to 6. In this case, part 1 and part 2 belongs to under part A, so the same condition shared here, so k equals to 6. You might want to say, okay, when k equals to 6, this is what I want to integrate. So we say x divided by 2 root x plus 6 equals to d dx square root of x plus 6 minus square root of x plus 6. Just rearrange this relation. And if I antiderive both sides with limits, 6, what I'll get is, I'll cancel out the ddx here. Just get, this is an x times square root of x plus 6. Notice that this x plus 6 here, when you antiderive x plus 6 under the square root, you're antideriving x plus 6 to the power half. So you add a power. Then you subtract, let's say, x plus 6 to the power 3 halves times 2 over 3, divided by the new power times 2 over 3 from 0 to 6. Then you just stop in the values. 6 root 12 minus 2 over 3 times 12 to the power 3 over 2. That's one part. Subtracting a 0. 0 times anything is 0 minus 2 over 3 times 6 to the power 3 over 2. And you'd want to combine everything, say 6 times 2 root 3 minus 2 over 3 times 12 times root 12 plus 2 over 3 times 6 times root 6. So what I'm going to do first is I'll write a 12 root 3. Cancel that out. This is 2 times 4 times 2 root 3 minus 16 root 3, something along this line. And 3 and 6 cancel out. You get a 2 times 2 is 4. And you add 4 times square root 2 square root of 3. Combine these two terms, you get a minus 4 root 3 plus 4 root 2 times root 3. Therefore, you get 4 root 3 as a common factor, then just root 2. Take away 1. Of course, I believe there are other equivalent answers, but you should show reasonable algebra and combine everything into, let's say, a relatively simplified term. Of course, this is the hands approach. We call it integration by recognition. For other capable students, if you are doing specialist math, you might want to do integration by parts. Yep, you can do that. What I'll show you is another technique. What are you trying to find is 0 to 6, x divided by 2 square root of x plus 6 dx. And you just say u equals to x plus 6. Du dx equals to 1. X equals to 0 gives you u equals to 6. And x equals to 6 gives you u equals to 12. Do a complete substitution, then this thing can be written as u equals to 6 to u equals to 12. And notice your simple x can be u minus 6. So you have u minus 6 divided by 2 square root of u du, something along this line. And then you just split the integral, like 6 to 12. u over root u, just root u divided by 2, minus 6 over 2, 3. 3 on root u du. And then you will get a half times u to the power 3 on 2 times 2 on 3 in the front, minus 6 square root of u, from 6 to 12. And then you get a 1/3 u to the power 3 on 2. Take away 6 root u between 6 to 12. So you can actually get a 1/3 times 12 times root 12. Take away 6 root 12. Subtracting, let's say, 1/3 times 6 root 6. Take away 6 root 6. So you could also get, for example, 4 root 12 minus 6 root 12. That's minus 2 root 12. And this is 2 root 6 minus 6 root 6. That's minus 4 root 6. But with a negative, you get a plus 4 root 6. Well, you might get some answer like that. And then you just take out, let's say, some root 6. If I take out 2 root 6 plus 4 root 6, you may well get a 2 root 6 bracket 2 minus root 2. I believe this is also an equivalent form. Like you can bring out the root 2 from each case here. You get a 2 root 2, etc., etc. So there are heaps number of equivalent format. Okay, like this. So you get 2 root 12 divided by root 2 minus 1, which is just 4 root 3 root 2 minus 1. Okay. Anyway, it's not an awfully challenging question. Yep, you could use integration by parts if you wish, as I explained, but you just get the same thing here. Okay, using integration by parts doesn't attract you more marks, etc., etc., as long as you get the correct answer. Equivalent merit. But part B is independent. Find 0 to k f of x dx in the form a minus root a divided by b, k times root k, where a and b are positive integers. So actually, this is a general case. I was wondering, what if you attempt part B first, then come back to part A2 and solving k equals to 6? That would be an interesting approach. Okay, so 0 to k, x divided by 2 root x plus k dx. Without reinventing the wheel, I know the structure is going to be x root x plus k, subtracting 2 on 3 root x plus k to the power 3. Okay, something like that. I'll just write it in the normal fashion, x plus k to the power 3 on 2, between 0 to k. And this was imitating whatever I did in part 2. Okay, just replacing the 6 with a k here. It's true. And then you get k square root of k plus k. That's 2k minus 3 on 2, 2k to the power 3 on 2. Take away a 0, take away 2 on 3, and a k to the power 3 on 2. You actually get a k root 2k minus 2 on 3 times 2k times square root of 2k, and plus 2 on 3 times k times root k. So the next thing you want to do is take out the root 2, put it as a k root k minus 2 times 2 times root 2, 4 root 2 divided by 3 times k times root k, plus 2 on 3 times k times root k. Okay, so You can actually combine these two terms because they have some root 2 here. And I might want to write this one as 3 root 2 divided by 3k root k subtract 4 root 2 divided by 3k root k plus 2 on 3 k root k. So you just get a minus root 2 on 3 times k root k plus 2 on 3 k times root k. Therefore, you bring out a common factor. You can put it at the front or put it to the end. So the A value is 2, B value is 3. Yeah, the problem is finished. And just as I explained, if you did on part B first, well, here is another alternative method. Alternatively, part B, we see that 0 to k x divided by 2 root x plus k dx equals to 2 minus the square root of 2 divided by 3 times k times square root of k, for k belongs to r plus. If k equals to 6, then 0 to 6 x divided by 2 root x plus 6 dx is 2 minus root 2 divided by 3 times 6 root 6. You can cancel them out. Don't forget a bracket. This is a 2. So you actually get, yeah, 2 minus root 2 times 2 times root 2 times root 3. Then you can bring out, let's say, root 2 minus 1 times an extra root 2 times 2 root 2 root 3. So eventually it's root 2 minus 1 times 4 root 3. Same answer. Anyway, I think, is there anything else I want to say? No, end of the exam questions. Overall, an interesting paper. This one was tricky, the idea of reducing sample space. Yeah, but it's a decent tree diagram, discrete probability function, a discrete probability question. Yeah, it's actually a geometric distribution. Well, shouldn't be that close to the asymptote. I'll just draw it nicer. Yep, should be fine. And I'm a bit fussy. This looks much better. The single smooth curve. Anyway, that's everything I want to say. Okay, I'll find another time to do other videos. All the best for your November exam preparations. Bye-bye.